My name is Sean Kramer, and today I will be discussing my research on memory mismanagement in C and C++, where we will look at the software attacks that target memory vulnerabilities and the current countermeasures in place to thwart them. Let us begin by understanding the focus of this research. It is broken into two parts. The first portion examines software attacks which target the C and C++ programming languages. We identify the cause of these problems to stem from memory violation errors and explain the difference between the two types of errors, spatial and temporal. Once these errors are known, we dive further into the topic of software attacks, specifically the ones that originate from taking advantage of memory violations. In the second portion of this work, we discuss the current state of security that focuses on the prevention of memory violations. Here, we look at how these security features work and note the drawbacks that prevent these countermeasures from widespread adoption. Beginning at the underlying cause of software attacks, we must first recognize and differentiate between the two types of memory access violations, spatial errors and temporal errors. Now, both spatial and temporal errors are caused from dereferencing a pointer, and depending on how the pointer is dereferenced, correlates to what specific error has been targeted. Spatial errors dereference a pointer to outside of its allocated memory space, whereas temporal errors dereference a dangling pointer, which is defined as pointers that do not point to a valid object of the appropriate type. The reason the two examples are starred is that they are very common and easier to comprehend than the other examples. In the bounds violation spatial error, an array of 100 is created, but further along in the code, the pointer p sets itself equal to the address of the 101st element of the array, which corresponds to a value that is out of bounds of the array's allocated memory region. For the dangling stack pointer temporal error, a global pointer p is created, and within the function foo, the pointer is set to the address of the local variable x. When foo returns, all local variables are destroyed, causing p to become a dangling pointer. By taking advantage of the memory violations described, there are four categories of attack that can be carried out. Code corruption attacks, as implied by the name, look to corrupt code by overwriting the program in memory. Control flow attacks modify a code pointer to cause the program to deviate away from its intended flow or to relinquish control over to an attacker. Control flow hijacking attacks are of most importance as they are considered to be the most common type of software attack in existence today. Data-only attacks look to modify only the program's data in an effort to gain more control or access higher privilege levels of a system. Lastly, information leakage attacks function to leak memory contents to gain additional information about the system. Oftentimes, information leakage attacks are used in conjunction with other attacks, as the attacker must first learn about the functionality of the system or program to find its vulnerabilities. Building off the last two slides, the image shown here is an example flowchart describing how memory violations can lead to the various attacks. At the top level, we have spatial and temporal errors, each caused by dereferencing a pointer. That pointer can be used to either write to memory, read from memory, or to free a section of memory. How that dereference pointer is used correlates to the specific type of attack category, with exception to the modification of data pointers, which are often utilized for the sake of creating additional spatial errors. Before moving on to countermeasures, I want to quickly describe how a spatial error works in the implementation of a control flow hijacking attack. On the right, we have a layout of a program stack created during execution. We see that function parameters are placed at the top, followed by the function's return address, previous frame pointer's address, and local variables. The goal of the attacker is to overwrite the function's return address with the value of another function in the code or to another arbitrary location specified by the attacker. By submitting a value to the local variable buff, that extends beyond its allocated space, the attacker will begin to overwrite the next data on the stack, which in this case is the previous frame pointer and the return address. Forcing the array buff out of bounds is a direct example of a spatial memory error. Fortunately, security researchers have developed a variety of different countermeasures to combat memory errors and the subsequent software attacks they cause. Hardware-based solutions are stack canaries and shadow stacks. It should be noted that these solutions can be implemented in software as well, but the benefit of using hardware is a massive reduction in overhead. Software solutions can be done at the source code level or at the executable level. For source code solutions, there exists address space layout randomization and pointer safety protections, while at the executable level, binary rewriting is a new branch of security research and can be done statically or dynamically. Beginning with the hardware-based countermeasures, stack canaries work by placing a random value, known as a canary, between the local variables and the return address. When a function attempts to return, the canary value is checked before the return is executed. If the value of the canary does not match, stack smashing is detected and the program is terminated or an error is thrown to the user. Shadow stacks are used solely for the protection of control flow integrity and work by making a copy of the function's return address and storing it in a separate part of the memory. When the function is set to return, the value of the return address is compared to the value stored in the shadow stack. If the two values match, the function is processed normally. If they do not match, the program is either terminated or an error is thrown. Moving on to software-based countermeasures, one popular solution is known as address space layout randomization, which gives a random offset to the code, libraries, and stack sections of memory during load time. Another option is pointer safety and is performed by identifying and encoding all pointers within the code with their base and bound addresses. This pointer metadata is stored in its own hash table away from the program's memory. When a pointer is called upon, its future address location is checked to see if it fits within the allocated base and bound area. Binary rewriting looks past the source code and focuses on protecting a program after it has been compiled at its binary level. The executable is disassembled to a human-readable format, and protections are then put in place where potential hazards may arise. For instance, boundary checking at the creation of arrays. This can be done dynamically, which is being performed during execution, or statically, which is any time between after the program is compiled but before it has been executed. Though these solutions can be effective, each method suffers from a significant drawback that prevents them from being adopted by industry. Stack canaries offer the weakest level of protection and only protect against buffer overflow attacks. Attackers can craft arbitrary memory writes which do not interact with the canary or use information leakage attacks to find out about the canary's value. This can also play into the mitigation of address space layout randomization. It is impossible to successfully disassemble an executable with 100% accuracy, making binary rewriting techniques susceptible to false results. Another drawback of binary rewriting is that the increase in overhead can be at least 100%, as some binaries require that the original executable file be contained somewhere within the original binary. Overhead is also a problem for pointer safety, as the size of each pointer triples by including its base address and bound address. Now, another drawback to them as well is that they are only effective against spatial errors, but do not provide any form of protection against temporal errors. Most importantly, almost all solutions require the source code to be present, making them incompatible with legacy software. Thank you.